working, but as previous time, I'm going to scan all the slides I'll show you today and upload them on Vision, just in case you won't be keeping up with taking notes. Don't worry about it. It will be uploaded. So we're going to talk about weighted graphs today and Dijkstra's algorithm. In case something is not very well visible, please don't be shy. Give me a shout. I'll be checking time to time, but it's not easy. So just if you don't see it well, just give me a shout. Is this somewhat fuzzy? Is it fuzzy? Yeah. So, weighted graphs are graphs for which each edge is equipped with a number called its weight. Let's write this down. Weighted graphs are graphs for which each edge is equipped with a number called its weight. For example, consider a graph which represents a road network in which the vertices they correspond to towns and edges correspond to roads connecting these towns. Then if we put a distance on each road, right, that will give us a weighted graph. So we will, talking about simple graphs, talking about weighted graphs, we'll focus on simple graphs. For which we will denote as W of U and V the weight of the edge UV. So this will denote And one problem which emerges in connection with weighted graphs is the so-called shortest path problem. So we would like to look at the weighted graphs with non-negative weights. And then we would like to find the path of the shortest total weight between two given vertices. So by the total weight on a path, I mean just the sum of the weights of all edges which belong to that path. So let's write this down. So this is called the shortest path problem. So we consider a weighted graph with non-negative weights. And we define the length of a path to be the sum of the weights of the edges to be the sum of the weights of the edges in this path. And the shortest path problem. Okay, going to move it over here. Continue here. Shortest path problem consists in finding the minimal length path or paths, there may be several, between two given points. Okay, firstly, I'd like to comment on all these conditions, like why do we want the weights to be in the negative in the context of this problem. And usually, if you think of the weight as, say, distance in roadworks or time it takes for a signal to pass through a connection between two nodes in a network, then there will be naturally no negative numbers. But also for the whole problem to make sense, you don't want to have negative weights, because you might have a loop with a total negative length, and then by going around this loop many times, you will be lowering and lowering the weight you have. So for the problem to be correctly posed, to begin with, you want no negative weights. Also, restricting our graphs to simple graphs doesn't significantly modify the applicability of the shortest path problem, because if you're looking for a shortest path, clearly loops are of no help, because they would only add weight, but you're not getting any further away from the vertex from which you're starting. So you can safely disregard loops. They won't be used for shortest paths. And also, if you have multiple edges, then clearly for the shortest path you need to choose the edge with the smallest possible weight given. So it's not really a big restriction to look at simple graphs in the context of shortest path problem. And it turns out that there's a very nice algorithm, which is really a classic algorithm in computer science, which allows you rather quickly to find the shortest path in any weighted graph. So this algorithm is called Dijkstra's algorithm, and Dijkstra spells like this. Dijkstra's algorithm. So it was discovered by a Dutch computer scientist. His surname is Dijkstra, and it was published in 1959. And so before I proceed with it, let me just ask how many people have not heard of Dijkstra's algorithm before? Have not? Quite a few people, yeah, thank you. Because I know it's in some schools, it's covered, right? So I'm going to explain it from scratch, and also the way I will be doing it and the features I'll be discussing. Hopefully it will be new material even for those who studied this algorithm at school. Okay, so how does the algorithm work? It uses labels. The algorithm uses labels, which we will denote L of B, which are defined for all vertices. Defined or specified for all vertices. And it runs in iterations. At each iteration, it will be changing the labels of certain vertices. So initially, it sets the starting vertex to have the label 0, and all other vertices to have the label to be given by infinity. Well, for practical purposes, just a very large number. Okay, but we'll idealize it and say infinity. So initially, the algorithm sets the label of the starting vertex. Let's call it A, to be L of A equals 0, and L of B equals infinity, or very large number, for all other vertices B. It also introduces a special set, capital S, called the set of visited vertices. It uses a special set denoted capital S and called the set of visited vertices. And at each iteration, it puts into this set, capital S, one new vertex. The one that has the smallest label available. So it has to be a new vertex, not yet in capital S, and it has to be with the smallest label available. So you can see the first iteration, if we start with 0 and infinity, then at the first iteration it will put the starting vertex into the set capital S. Okay. So let me write this down. That's a general prescription. At each iteration, the algorithm puts into S one new vertex, the one with the smallest label, capital L. After it does this, it updates the levels of the remaining vertices, which are not in capital S. After that, it updates the labels of the vertices not in capital S. How does it do it? Well, I'll explain in a moment, but it stops, the algorithm stops when it puts the final vertex Z, which is supposed to be given, the final vertex in the path, when it puts it into the set capital S. So it stops when it puts the final vertex, denoted Z. So the path goes from A to Z, from the final vertex to from the initial vertex to the final vertex. So we stop when we put Z into capital S. So how does the how do we update the labels? Updating the labels. So suppose, yes? suppose U is the vertex which has been just put into S. Right. Then, if V is not in S, and V is connected to U by an edge UV, so we reassign the label of V to be given by the minimum of the old label, whichever one is smaller. The old label L of V or the sum L of U plus W of UV. Okay, so if L of V is less than L of U plus W of UV, then L of V is unchanged. And if L of V is greater than L of U plus W of UV, then the new label of V is L of U plus W of UV. Okay, so that's the general rule. And let me now illustrate this on an explicit example on a graph. So there are many ways to record Dijkstra's algorithm. Right? Probably at school you were taught to put some data next to the vertices. In the type notes, there is also one notation suggested when you record only the labels which has been changed. So here I will explain a third method, which is probably more tedious, but it really helps you not to make mistakes. So I will put everything into a table, and in this table, in the left column, I will record the vertices which are in my set capital S, the set of these vertices. And in the other columns, I will record the labels of individual vertices. So I'll list all the vertices I have in this weighted graph: A, B, C, D, E, F, G, and Z. So A here, this vertex, is our starting point. Z is the final point here. And we're supposed to find the path of minimal total length between A and Z. So we start with the set capital S being empty. So I put an empty set here, and the initial vertex is given the label 0, while all other vertices have infinite label. So I put the infinity sign there. Now the algorithm starts each iteration by taking the vertex with the smallest weight available. So the first step is always putting the vertex A to my set capital S. So I write A for capital S. And once you put a vertex into the set S, its label no longer changes. Either you just remember it, or for myself, I use this system when I box the labels which no longer are supposed to change. So the label is 0, and I put that 0 into a box, which means that it shouldn't be changing anymore. You can continue writing zeros in boxes in all the next iterations, or you can just stop here And remember, right, that the label freezes at that stage. Okay, so we put the vertex A here. Next, we should update the labels of the remaining vertices. And we only need to bother checking for updates the vertices which are connected to A by a single edge. So E, D, C, and B. Right? Because G, F, and Z are not connected by a single edge. So for them, the labels will remain the same. So I can definitely write that it's infinity for Z, infinity for G, and for F. For the other vertices, B, C, D, and E, I should compare the old label, which is infinity, with the label of A, which is 0, plus the weight of the connecting edge. So clearly that will be some finite number, which will be smaller. So at this stage of the algorithm, those labels are just changed to the values of the corresponding weights. So for B, it becomes 4. For C, it becomes 7. For D, it's 4. And for E, it's 2, right? The corresponding weights on the graph. All right, so I'm done with my first iteration. Now I repeat the same steps. So I check the unboxed labels and find the one with the smallest value. That's clearly E. So E I add to the set capital S. So I put now AE. And once I've done that, the label for E will no longer change. So I'm going to box it. Okay. And next I check for updates. So the only vertices which are connected to E are A, but A is already in capital S, D, and Z. So the label for D, I should compare the old label 4 with 2 plus 1, which is 3. Right? 2 because it's the label of E, and plus 1 because that's the weight of the connecting edge ED. So 3 is smaller than 4, therefore I change the label of D to the smaller value of 3. For Z, the old label is infinity, so now definitely it's going to change to a finite number. So the weight of E is 2 plus the weight of the connecting edge, sorry, the label of E is 2 and the connecting edge has weight 12. So for Z, we change from infinity to 14, which is a smaller number. And the rest of them will remain the same because they're either boxed or they're not connected to E. So I put infinity, infinity here, 7, 4 for those, for B and C. Okay? And we repeat. So we now look at the all of the unboxed labels and find this, the smallest one, which is 3, is the label of D. So I put D into the set S, and I box it, just as a bookkeeping mark to remember that it's not going to change anymore. So I might, you might also want to circle out the vertices which are already in the set capital S directly on the graph, just to remember which ones to update, which ones not to update. So I've just put in D, which is here, and it's the only new vertex it's connected to is F. So the label for D is 3. 3 plus 5, that's 8. So the label for F will change from infinity to 8. Okay? And the other vertices will have the same label. Right, next I check the label, smallest unboxed label 4, 7, 8, infinity, and 14. 4 is the smallest one, so I add B to my Z capital S. So we add B, the label 4, which now is boxed, and we check for updates the labels of C and G. So for C, 4 plus 2, that's 6. That's smaller than 7. So I do change that label from 7 to 6. For G, 4 plus 6, that's 10. And that replaces the old label, which was infinity, right? So we put in 10. And that's that, because no other vertices are connected to B, right? Just C and G. Right, so I copy the rest of them. 8 and 14. Okay, bear with me. I need to do 3 more iterations, and then I'll talk about, you know, what can we read off from this algorithm. All right. So next iteration, 6 is the smallest label, which corresponds to C. So A, B, D, B, C. And that becomes boxed. And on the graph, C is here, so it's connected by single edge to G and to F. So I check. So 6 plus 4, that's 10. But that's larger than 8. So I don't change the label of F. I only change it when I get a smaller value. So it remains 8. And for G, CG has weight 3. And 3 plus 6, that's 9. 9 is smaller than 10, so we do change that label to a smaller value 9. Okay, this is still 14. Right, so I have only three remaining vertices. Now the smallest label available is that of F. So A, E, D, B, C, we put in F. And on the graph, F is here. So I box 8. And I check 8 plus 4, that's 12. That's smaller than 14. So I change the label of Z to 14. For G, F is not connected to G by a single edge, so it remains 9. Right, last step, because only 2 vertices are left. And the smaller label is that of G. So A, E, D, B, C, F, G. 9, box it. And then we check. So we put in G. It's connected to Z, the only remaining vertex outside capital S. And 9 plus 3 is 12, which is exactly the old label. So, well, it clearly remains with 12, but this tie, which happened here for the first time, which I didn't address before, actually signifies something. It signifies that the shortest path is not unique. There are 2 such paths. Okay, but so next, so I'm done because at the last step I put in Z, and its label is 12. Right, so A, E, D, B, C, F, G, Z, and the algorithm stops. So what can I now read off from this table? Firstly, it's very simple to read off the length of the shortest path. So that's the label of the final vertex at the moment when I put it into the set capital S. So it was changing here a couple of times. 12 is the last frozen value. That's the shortest path length. Okay. So that's what we immediately read off. That's easy. As for the path itself, then there is a certain procedure to find it. And then we'll see that we actually have 2 of them. So how to find the shortest path? write down that firstly, when we put Z into capital S, its label L of Z gives the length of the shortest path. Sorry, again, yeah, thank you. Of the shortest path. Okay, then to find the path itself, find the path itself, we start from the last vertex and then we build the path going backwards. We start from Z and build the path backwards. So let V sub I be the vertex we already have in the path. A vertex already in the path, say initially just Z. We want to find Vi minus 1, the vertex before it. We find the iteration in which V sub I was reassigned the label for the last time. So find the iteration in which V sub I was reassigned its label L of V sub I for the last time. If that happened when we added a vertex U to the capital set S, then we set the previous vertex in the path to be U. Okay, if that happened when we have added a vertex U to capital S, we set Vi minus 1 to be equal to that vertex U. We keep going backwards in this fashion until we reach the first point of the path, the initial point of the path. We keep backwards in this fashion until we reach the initial vertex A. All right, so how does it look for this graph? So I start going backwards from Z. So I have to look at the situation when the label of Z changed last time. Well, similarly it was when it changed from 14 to 12, but remember the tie. So the tie happened at the last step when we added G. So you can think it's kind of a tautological reassignment. So that gives you two options. Either you go back to F, right, because that was the jump from 14 to 12, or you go back via G, because that was changed from 12 to 12 when the tie happened. So let's explore both of situations separately. So if I go back via F, then to find the vertex before it, I check the column of the labels for F here and see when the label was changed last time. It changed from infinity to 8. And going horizontally, I see that happened when we've added D. So D is the vertex on the path before F. Next, I check the column for D and see that it changed from 4 to 3. And that happened when we've added E. So E is the vertex before D. And the label for E changed from infinity to 2 when we've added A. So I have arrived, going backwards, I have arrived to the initial vertex. So that created one shortest path. And if you add on the all the weights, so let's do that. So AE has weight 2, ED has weight 1, DF has weight 5, and FZ has weight 4. So if we add them together, 2 plus 1 plus 5 plus 4, we get 12, right? Which we already knew that's the shortest path length. Okay, that's one of them. Let's mark it on the picture. So it's AE, and then ED, DF, FZ. Okay. There's another one which goes backwards via G. Right? And that happened because we had that tie. The old label was the same as the label of the vertex we just put in plus the connecting weight. So for G, if I examine this column, I see that the label changed last time. It jumped from 10 to 9, and that happened when we've added C. So before G we have C, and examining the column for C, I see that the label changed last time from 7 to 6 when we added B. So B comes before C. And examining the column for B, we see that it changed from infinity to 4 when we put in A. So that gives you an alternative shortest path which goes from A to B, and then from B to C, and from C to G, and G to Z. Okay. And both length, its length is also 12. That can be easily checked. Okay, so that's how you learn from the table the length and the shortest path itself, or it may happen when some coincidences are taking place. It can happen that there are more than one shortest path, so that's how you can find all of them. Are there any questions about executing the algorithm, how you run it and how you read off the paths? Okay, then let me explain some features. Just make some comments. One warning is that sometimes, there is some misconception that this sequence of vertices, right, the final content of the set capital S actually gives you the minimal path, right? And you can see why you may be tempted to think, because it starts with A and ends with Z, but it has, in general, has nothing to do with the shortest path itself, right? It's just how the algorithm runs, but the shortest path is encoded in a more complicated fashion in the table. Okay, so just a warning that this sequence, in general, it's not even a path. If you look at A, E, D, B, C, F, G, Z, it might not even be a path at all. Okay. Right, so some general comments. Well, on the algorithm. First, I'd like to say that it belongs to the class of algorithms which are called greedy algorithms. Algorithm is a greedy algorithm, which essentially means that it utilizes a certain local strategy. So whatever is available at the moment you're doing the iteration, you go for some smallest value. So I didn't clearly explain what these labels, I mean, these labels, they have a certain meaning of lengths, right? So if you're a very greedy person, you want the smallest possible length, you should go for the smallest possible label available, not thinking how your current choices might affect your future choices. So there are more sophisticated strategies, like dynamic programming, which don't just locally decide to go for something, for the best available option at the moment, but they weigh in a more complicated way they see how your current choices can restrict your future choices.